Hi, I'm Leanpub from Leanpub, and in this episode of the Leanpub podcast, I'll be interviewing Edward Abramowich. Based in Singapore, Ed is a best-selling author who has partnered with leading energy majors, aerospace, automotive, and high-tech companies to deliver transformative business performance improvements. He has worked extensively with executive teams and organizations worldwide, guiding them to adapt and thrive in a rapidly changing global landscape. You can follow him on X at EdwardAbram88 and check out his website at straitsconsulting.com. Ed is the author of the book, Rethinking Capital Project Delivery, Agentic AI-Driven Strategies for the New Era. In the book, Ed challenges everything we take for granted about how mega projects are scoped, funded, and executed. In a world of accelerating change, static delivery models fall short. This book introduces a new approach that is adaptive, agentic AI-enabled, and product-driven. From digital twins to agentic AI, discover how leading organizations are shifting from build and forget to build to evolve in this book. So thank you very much, Ed, for being on the Leanpub podcast again.
Hey, thanks, Len. Thanks for the great introduction as well. And it's been too long since we last spoke.
Yeah, so I was just going to say, normally I like to begin these interviews by asking people for their origin story, but we went over that, and I think moving to Japan and stuff like that when you were younger, in our first interview a couple of years ago, so people can find that easily enough online. So I thought we'd just begin with me asking you what you've been up to in the last couple of years.
Right, last couple of years, it's been two mega deep water projects for an energy major, engineering and construction of these. They're each about $6 billion each projects. And right now we're finishing up another project, which is an offshore gas platform. And again, so I've been deep into this world of energy projects where, energy majors, whether it be gas or nuclear, or, you start with a concept, we'd like to build a particular asset. And then that concept, goes through this engineering evolution to eventually construction. So last 2 years, it's been two deep water platforms, one gas platform in far remote Western Australia, offshore.
Is that the Crux one? Just so the Shell Crux project, so we can give people something to look up online.
Well, we can, yeah, but I don't want to reveal too much of that Crux.
No,
But sure.
I just so people. I was just checking out the website. There's a website that's has some pictures and stuff like that. So people who aren't familiar with it, this kind of project, you can have a kind of floating platform that's engaged in oil and gas activity, and you can have pipelines that go to land, and they're huge projects.
Yeah, and I think all of these projects actually, there, whether it be offshore or nuclear or mining, they all actually follow the same sort of engineering approach. And it's very sequential, very stage gate.
Right.
So each project has a similar sort of dynamic. And what I began to notice over time was sort of what's common between these projects. And one thing that's common across all of these projects is 99% of the time they miss their schedule and they cost overrun. And so some people in the industry started saying, well, what's going on? We're spending billions of dollars, and why are these projects consistently the schedule blowing out, and why is cost overruns always the case? So that led me to start going down this path, which eventually resulted in this book.
Yeah, definitely. And I just wanted to give people, so we've heard, the scale of the individual projects, sometimes 6 billion, sometimes they can be 10 billion, sometimes they can be even more. But you gave a great talk on YouTube that I'll hopefully remember to point people to in the show notes and things like that, about how these big capital projects that we're talking about in aggregate are something like 25% of global annual GDP. Like if you just add up the spending on them, and you say, something like 98% over schedule. What is it? Over schedule, over cost, over and over again, is the joke that I think that you make. And that these projects can take 7 to 10 years, and that they're also very kind of, they're not very profitable. They have a low profit margin as well, which is something else that they share. So we're talking about like huge amounts of money and kind of like very transformative projects. For example, one I know that you talked about that I found a Wikipedia article for was a proposed solar project in Northern Australia, and then a power line to Singapore, which reminded me of something that got me excited when I read about it. There's something like a solar project in Morocco that might send a power line to the UK. I read about this a couple years ago. Now, for anyone who's ever been involved in these things, the projects, are sometimes bigger in the eye of the beholder than they end up in reality or whatever. But you got to start big with big vision. But solving the problem of these projects going over budget and over time would hugely improve productivity globally.
Yeah, absolutely. And the world's, demand for energy is increasing, manyfold. And so and of course, sustainability and, how are we going to move off, fossil fuels, or how are we going to get into more sustainable energy? To me, it's an engineering issue. And we need to get much, much better at these sort of projects. So, that over schedule, over budget, over and over again is called the iron law of capital projects. And it comes from a lot of research, which basically pointed to the fact that, these issues are it's commonplace now, so much so that it's given its own iron law.
Mhm.
What I did though was I started to look at these projects and say, well, what's really going on here? What is there something which is well, there is something systemically wrong, because it happens across all projects. So the question then is, what is that? And to answer that, then I started to look around and say, well, has anyone actually solved this problem before? And it turns out they have in the tech industry,
Right.
aerospace and technology.
Yeah, specifically the case study that you give in the book, and one that people may have heard of, is Tesla's gigafactories.
Yeah, I'm not sure. When I speak to people about the Tesla Gigafactory, not many people actually know about it, but they know Tesla the car, and they know Elon Musk. But what they're able to do in these gigafactories is quite phenomenal. And if you look at the engineering philosophy, it's at its core, it's a very different philosophy than what most capital projects are following. And for those who are not familiar, so Tesla went from an empty plot of land in Shanghai. This is the Tesla Shanghai factory. So you can imagine, like these factories are huge, right? An empty plot of land, and they went from an empty plot of land to manufacturing the first Model Y car in 11 months. And by the way, they were actually designing the Model Y at the same time. So these factories are so huge and so complex. Imagine the complex production lines, imagine all the robotics and building the factory. And that was done in 11 months, which is phenomenal. And they did the same in Germany and in the US. I'm referring to sort of an adaptive engineering model where it's all about speed to first value.
Mm.
How do we generate value incredibly quickly? And when you put the lens of speed to first value, you end up with things like Tesla Gigafactory.
Yeah, one thing I know you talked about is how, engineering phases that may in the past have taken years, like, are now happening much more quickly, perhaps in months and things like that. And one thing that you really struck me there was when you said that the car was being designed as the factory was being built. So the design for the car was not yet finished when the factory was being built. And so the factory presumably had to be able to, the construction of it had to be able to adapt to changes in car design as the factory was itself being built. So the adaptation has to be built into the process for the big project to succeed.
Yeah. So the core issue is that old styles of engineering, they assume you can predict the future,
Yeah.
but they assume that in 6 years' time, I'm building this platform. I know it's going to look like, and of course, it never does, and things change, and so at its core, these old engineering processes they were formed around governance and compliance. It was making sure that people were compliant to process. It wasn't about adaptability.
Right.
And So what it means then is using the old model, you're guaranteed to produce something that you don't want. Whereas in the Tesla model or SpaceX is the same, or even Saab is saying, well, no, we let's assume that we aren't able to predict exactly what it's going to be, because technology is changing too quickly, requirements are changing too quickly, and so instead, why don't we figure out how we can engineer, be faster, and be adaptive.
And the Saab example, I believe, is fighter jets, right? So we've talked about cars and car factories and platforms, but it's affecting all areas of huge capital project production, especially in
So,
ones where life and death is directly.
yeah, so Saab Aerospace, and I'm remotely connected with these engineers working on this project now, and so they're building the sixth generation fighter aircraft at the moment, and they're actually flying it now, but nothing's been built, and they're testing stealth paints. They're testing different engines on this plane which hasn't been built, and it's like, well, that's not, how's that possible? And so what's happened is technology has got to a point now where through digital twins, you're able to actually iterate in this cyber physical world, and it makes things incredibly quickly. Now, if I translate that to a capital project, like an offshore gas platform, for example, so we would spend a year and a half in kind of a concept select phase, which means you're thinking about, oh, what should this thing be? Should it be something floating? Should it be on should it have a jacket, be on the ground? So after about a year and a half of that, then you start to say, okay, so we have the concept, and then we start to figure out what's the economics of it, and you go through this process of called front end engineering design, and there's another year and a half going, right? So 2.5, 3 years. Then you make the decision. Okay, this is what we're going for. This is the high level processes and engineering is going to be like, and then you enter into detailed engineering, which is you're really now getting into the detailed engineering. There's another 2 years. So maybe 5 or 6 years in this engineering phase. If you're to take this model that people like Saab or these AI driven models and apply it to the same, those 5 or 6 years you could do in maybe 5 or 6 months. And if you had, I'm not saying it's easy, it's having the data and availability. Now, every day a large gas asset, which let's say that every day it's delayed for whatever reason, the asset owners is losing, I don't know, $10-20 million a day. That's a lot of money. And if you can shift it from years to months, well, it's happening, right? And so in this world now, you have these energy majors kind of struggling with their legacy systems and looking around and saying, wow, this is what other industries are doing. So how do we, what do we do? How do we think about this? And that's kind of what the book's trying to get to.
Yeah, you just triggered an old memory in me of when my old days as an investment banker, when I was doing financial analysis for like project finance for a giant LNG kind of project, and thinking about like sensitivity scenarios, as they're called, where you kind of like, you can see the impact on the to use it like the IRR based on when the project was finished in your model. And like, yeah, that's definitely true. Like one day can be millions of dollars, delay, and but years delays then means entirely. And like a lot of those projects could be very political. We just had a big LNG project, liquefaction project finish up in British Columbia in Canada. That was started by Malaysia. And that was, like, so there's this sort of geopolitics get involved, and project delays can, affect politicians and things like that. So being able to speed up these timelines is not just about, profit. It's about getting that energy out there sooner. making people look more credible, everybody who got involved in the project, getting taxes to the province or the country that, or whatever, however you want to call it, that, that the people from that region will then directly benefit from. There's just so much at stake. Which is the part of the inspiration of the book, is there's so much at stake. And the question of why do these projects go over so often, and it's these legacy things you talk about. But one of the things that struck me about your book, um, this not being my field, is so much of what causes the kind of delays in and problems in the traditional way of doing things is psychological. You have a section where you talk about the psychology of persistence, system justification, and even very personal things like career risk asymmetry, where, I'll just quote it here: deviating from established methods is personally risky, even when those methods consistently fail. And so this change that you're talking about in your book means changing people's mindsets and approaches to things like risk and adaptability and things like that.
Yes, it's a totally different culture, right? And when you go down to understand, that sort of risks, it ends up you're kind of changing the entire organization, right? So leadership needs to be different, and so a classical capital project, the very hierarchical leadership, and this power resides at the top, and they make the decisions, and the people in the field, or the people doing the work, are just meant to stay in their cubicles and just do their job. And even the notion of teamwork, that kind of doesn't make sense. It's like, well, why do I want teams? And it goes back to, you know, Frederick Taylor, and it goes back to this sort of micromanagement culture, which hasn't changed much in capital projects world. The idea is, very hierarchical, very siloed. But what that means then is that as an individual, if I'm an engineer, if I make a wrong engineering decision, I get punished.
Yes.
So I will spend a lot of time to make sure I do not make that wrong engineering decision, even though it impacts. I'm not necessarily punished for the schedule of slipping of this, multi-billion-dollar project. So the incentives are different. So when you dig into this, then you need to start to think about the cultures, the incentive schemes, and how do you get really fast and adaptive. And it turns out that what you're looking at is like a fundamentally different type of organization, much more like a high tech type company.
Yes, yes, and that hierarchy thing, issue, it's come up in some discussions I've had with people in other areas. But the idea, I think something you said in one of the YouTube talks I watched before this interview, if you have to ask permission to do something, you're causing a delay. And
Yeah.
if everybody involved is waiting for decisions coming from the top in some kind of, compliance heavy way, then there's just delay is built into it, and then you can't build an adaptive system.
And people will recognize that. I've seen big projects where very early on in the engineering, people actually, they know the project's going to slip a few years ahead. They already know it. And then they know the project will slip. Then the question is, well, why don't they do anything about it? And in fact, all of the issues, they're not new. We know what's causing these slippages. But the point is they're not driven to innovate here. It's not an innovation culture. It's a compliance, culture. And you are to follow the process, because the process has been designed to make sure that we don't, have major engineering issues. But it turns out it creates them. It's changing decision making to where it can be best. Best decisions come from is another core concept.
And changing these kind of processes in this way also changes, from what I understand, where, and it's sort of very kind of, in a very interesting way, changes where the value is in your organization and what you're doing. So for example, if you're testing something that hasn't been built, data is very valuable, and you're testing your virtualization or your digital twin technology is itself where a lot of your value resides once you adopt one of these processes.
Yeah. So some of the things I'm helping energy companies with now is, there'll be certain engineering tasks. So let's take, for example, something called a hazard analysis. So usually early on in these projects, you might have a bunch of pipes and you might have pumps and systems. And what engineers will do is they'll list out all of these particular systems and say, well, okay, so what could possibly go wrong here? Could this pipe lose containment? If so, what is it we can do to make sure that doesn't happen? So they go through this process of hazard identification, and they start to figure out, okay, so how do we mitigate it? But think about this a little bit more carefully. So firstly, it's a one-off workshop in the current engineering approach. Everyone goes into a room, there's coffee and donuts, and then everyone starts to brainstorm these hazards. So a lot of it depends about the people in the room, right? How much experience they have. Usually, the engineers in these projects are formed, they're just on a contract basis, right? So they get who they can, and then they're on a contract basis. Then they move off to the next project. There's no sort of longevity of these teams. So what it means then is then the people doing the hazard, they may get stuff, they may not. It's a one-off event. Once they do it, it goes into an Excel sheet, which may get revisited later on. But now with things like Agentic AI, so if I'm in that workshop, there's also an AI agent in that workshop. And that AI agent is now basically kind of taking ownership of this hazard. So the team is starting to say, okay, so here's a pipe. So the agent, they're communicating with the agent who's building up data and knowledge about these hazards. But the agent also has access to data from all the previous projects. So they had infinite experience about this, where it's not like the individuals in the room. So what happens then is that what was a one-off tick the box task becomes a living system. And to do that, a team that's working with needs to be thinking about what data should we be capturing. How do I build trust in this algorithm so that we know it's doing the right thing? And so the team starts to work about how do they curate data, how do they test the algorithm, how do they get it to the point where it becomes, yes, we know it's going to make better decisions than us. That's a very different way of working.
Yeah, that's very interesting. That really struck a chord with me based on something I'd read about, the kind of one old way of doing things is the kind of one and done kind of approach to things. And now given that great explanation, I understand where the AI agentic element comes in, I think, in a very direct way. That was a really great example that, like, if people have dealt with a certain hazard in the past, there might be the team comes together and the team goes apart and takes all their knowledge with them. And there might be some result, typically in lots of these cases, some documents, some Excel spreadsheets, stuff like that. But, to draw from maybe the sort of ordinary experience that people might have with kind of using kind of AI, if you can go back to the link where all of that work was taking place, let's say with ChatGPT or something like that. If someone else can do that a year later or 2 years later when they're addressing a similar issue, you've kind of you can duplicate and reproduce automatically all that work that was done before, and then apply it to this new situation that you're in without having
Yeah, and
to end everything completely.
and that's just one example. So if you talk to as part of this book, I've done a lot of interviews and discussions, and there's these firms called engineering, procurement, construction firms, EPC firms, and they are specialists in engineering these. And if you talk to them, they'll kind of let you in on how things really work in practice. And so an engineering firm might have made, 10, 20 different like floating processing units. And so when a client goes to them and say, wow, you guys have made so many of these things, you're obviously very good at it, and because you do so many of them. And that, I guess that makes sense. But then when you talk to them and putting on this sort of data lens that we've been talking about, so they form a team to work on this massive floating asset. And that team may have had experience with it before, or maybe not. Again, it's a new team, so they come together. Then maybe in another part of the organization, they are working on a similar asset. But actually, the policies of these organizations, they're strictly not allowed to look at other people's data.
Right.
So then what it means is that this team says, okay, look, we can't look at an active project. Well, let's look at all the 30 projects we did before the same. But they don't have the data because it's basically been shelved and put into the data graveyard where it's never to be seen again. Mm-hmm. So in essence, they're starting the same engineering from scratch every single time. Now, if you were to take a different perspective and say, well, is there a way that we could use this data to continuously learn and adapt? You would truly get faster at that. They're simply not set up for it.
And so what can you set up if you're in like a sort of like incumbent existing big company that does those kinds of things? I have a friend who used to work for one that made floating offshore terminals, and he talked about how like he was like, I've got to make sure that this wasn't an offshore one, I don't think, but I've got to make sure a kind of screw from Connecticut gets to a platform in Nigeria on the right date. There's a lot of conservatism built into sort of those kinds of processes. How can you, if you're in an organization that is operating according to these past practices and say has the kind of data oblivion or graveyard, what can you do to kind of change that?
Yeah. The This all these recent surveys about capital project delivery. So McKinsey's done them, Boston Consulting Group, Accenture just came out with one, and they're all basically saying 99% of these projects, or between 95 and 99% of these projects, are always slipping schedule or cost overruns. And the reason why is because their engineering models are entrenched, and people, if I'm overseeing, I actually had a conversation recently with a company that's about to invest $40 billion in an offshore project, offshore, onshore in the region. And they look at the system and say, well, we know the system's broken, and but change is kind of, we don't want to break it further, and we're scared about how we can change this. And when that is so entrenched that it's extremely difficult for any executive to make a decision, we're going to try a different approach. Having said that, I think it will be forced on them, because what AI can do now is so radically different. It will break existing business models. And so if you're an energy major now, I think we better be really worried, because it's entirely plausible that we won't be using hydrocarbons for energy in the near term. If you look at what companies like Rolls-Royce are doing now with their modular nuclear reactors, nuclear fusion is happening, and maybe not long before it scales. So I think we're in this world now where there's disruption is so radical that legacy models will simply dissolve away. And if executive teams have the courage to be able to say, look, okay, we can see this coming, what do we need to do? Then they need to start planning, areas that they can start to impact their organizations, whether it be choosing a small pilot area or implementing it. And at the same time, the AI front is really interesting. I work with the top strategy consulting firms, and if you listen to these guys, and they're split about AI. they're saying, look, all of our clients are saying AI is not delivering. We're investing all this money, AI is not delivering. And then at the same time, they're like, well, we know it's going to, although people are using AI for personal use, and we know it's going to be a radical game changer. So how do we navigate this field? That's what I'm trying to introduce in the book, and that's the challenge which these energy majors are facing. The good news is that I think within not too long a period, we will have radically new sources of energy and more sustainable, and it will be driven through technology advancement.
And it will involve technology advancement, but like re-engineering engineering processes. Like for example, I believe I had a guest on a little while ago who worked at a Tesla factory. I think it was in Japan. And what he was describing, just like I'm only a kind of like, pub table kind of news follower when it comes to car technology and stuff like that. But, the fact that they could implement a change in design to a car the same day
Yeah.
is just like, you have to be doing things radically differently in order to do that. And that they also, they were like, there's like, Tesla had a kind of AI kind of, uh, I don't know, kind of central hub or something like that was learning from everything that was happening in the factory all the time, and was learning from every car that was being driven around at the same time. It was learning what happened when the new part was deployed in a new car that went out yesterday at the same time, and has been doing this for years. If you're sitting in a company that hasn't done any of that yet, the burden is great upon you to
Yeah.
adapt as quickly as you can.
Yeah, I'm not sure how many billions Tesla is spending on AI, but it's massive amounts of money. And that working dynamic, I looked very closely at what people like Tesla were doing, and how a traditional automotive manufacturer to introduce that change in a part. So let's say I'm on a production line, and maybe there's some part in the cooling system or something that we maybe it's not performing well in the field. It's getting hot or something.
Mhm.
Then this team, so the vehicles, they have live telemetry from vehicles in the field. A team will form on the fly. Not just that, they then re-engineer it on the fly, introduce it into production lines within hours. And by the way, Tesla is considered slow now.
Really?
People like BYD in China
Right.
are dominating. And if you look at Tesla, they only have a few different models. BYD is doing this on massive number of models. I know one of these top strategy firms is currently working with one of the main automakers, and they're all talking about what's happening in China automotive as absolutely phenomenal. So things are getting faster, and we need to get much, much better at adapting and learning. And that's at the core of the challenge. So what does that mean in an organization?
Yeah, and that was going to be my next question. So you have a section in your book where you talk about the traditional model, which is think big, start big, learn slow, and the adaptive model, which is think big, start small, and learn fast. So I'm curious about that. What does learn fast mean in this case?
So when I dug into this, if you look at a variety of capital projects, right, there some are, we know very, very well. So we know, for example, how to put up a solar panel.
Right.
And if we want more, we put up more solar panels, right? We know, we've learned from best practices. We know what to do. And in that case, it's able, you can actually predict it out and really plan it. And that legacy model does work well for this. It's when you enter into something where actually things are changing too quickly. The system is what we refer to as a complex system, and things are emerging, things are changing. So we can't actually predict. In that case, the legacy model breaks. And what's happened in industry is this legacy model it worked well for many years, and times were easier and things weren't changing, but it's now straining. And so the idea of think big is design everything up front, try and do the perfect design, and then implement it. Whereas
Right.
what you're doing is you're making assumptions early on, which when in this fast moving world, when you know least about the situation. So then the other model says, well, assume that you really don't know. You know what the end state's going to be. You know the direction. You know what you've got to build at the end of it. And you know more or less how it has to perform. But you don't know how to get there. And so in that case, it's all about how do you learn fast? How do you learn fast? And that requires getting feedback. And let me give you an example. This comes from the Ministry of Defense in the UK. And when they're building these complex systems, what would happen is that they would plan the system out many years in advance and say, we're going to build this system. Then costs would overrun, schedule would slip. Then the government would then intervene and say, oh my goodness, what's happening? Please give us something. Just give us something. All this money we've spent is getting blown. Just give us something. So the engineering then basically starts to pull together something. Okay, here's something which we can use. So it's happened so frequently that these engineering houses are saying, well, instead of pretending it's not going to happen, why don't we plan it that way? So instead of trying to, you might plan this big system, but you'll say every 6 months, I'm going to give you something which you can use, because we were doing it anyway.
Right.
So they've changed their engineering to be, I will give you something which you can use. You use it, and then we get feedback about is it working or not. Then they iterate. Mm-hmm. So that's moved from a monolith building a one and done to now trying to create in smaller increments and getting feedback. That was forced on the defense industry just because it was so inefficient.
Yeah, that's really fascinating. I was just sort of thinking of, I had an interview with Jeff Sutherland maybe since we spoke, and I learned a lot more about Scrum and the importance of delivering along the way.
Yeah, so I mean, Jeff continues to be a genius in this, and he's now working in technology, doing his own technologies. But in a way, also what Scrum and what these old models they need to adapt. They need to move beyond this, and I work closely with the Scrumming team. Mm-hmm. And if you look at really super agile companies, they don't do any of that. They don't do Scrum. They don't have product owners. They don't have Scrum masters. In fact, what one case study in the book is the Chinese appliance manufacturer, Haier, and it's phenomenal what they've done. Essentially, I think they had like 80,000 employees. They removed all layers of hierarchy, all layers of management, and they created 4,000 small teams. And there was like 2 rules of the teams. And one is you are directly connected to the customer. Right. So you get directly connected to the customer. And then the other was essentially, it's up to you what to do. If you're going to spend money on this, fine. So what's happened is these teams, if they don't generate value for customers, they don't survive. They get morphed into, the different parts of the company, or so what they've managed to do is create these like micro corporations, which are incredibly fast and agile, and the whole organization is constantly changing. the point of it is any hierarchy you have is too slow, it's too rigid.
Right.
And what's emerging out of this is something much, much more fluid and dynamic. And Hayer is a great example. And a lot of these organizations are kind of built around these micro teams now.
Yeah, it's very interesting when you talk about that, being adaptive and getting better. There's this chapter in your book or a section in your book called Iteration Over Perfection. And where you talk about, in particular, about modularity, which is kind of happening at the organizational level, I imagine, when you're kind of in a certain way, when you're splitting up into 4,000 teams. Well, what's a team? How do those teams report? How do they interact with customers? Things like that. And so I wanted to ask you a little bit about modularity, maybe in that kind of confusing meta way. But like, how does modularity help with iterating?
Yeah. So modularity is one of the core concepts. So if I can build something, so on one hand, let's look at the latest nuclear reactors. So Rolls-Royce, GE are creating these nuclear reactors, which are small, modular. They're like Lego. So you can actually build them in a factory. So you if you want a new power source, and I'm pretty sure most of the AI data centers will be using these, what happens then is you get a small unit, and then that power you can increase by adding more modules. And so what it means is that you've broken very complex systems into small manageable parts.
Right.
And when you break it into something manageable, then you're able to at great speed iterate and engineer on it. So the old systems were very tightly integrated. So if I was missing a particular system or part, the whole thing broke. I couldn't do anything. And well, to give you another, like the Saab aerospace example. So Saab jets, what they're saying is, well, we want to build a fighter aircraft or jet which can, in 10 years' time, be the best in the skies, but we don't know in 10 years' time what the avionics systems are going to be like. We don't know what the engines are going to be like, because they're going to get better. So instead of committing to an engine now, they create a system which is very modular, so they can take out an engine, put in a new one. And so people in Saab can actually replace an entirely new engine, 3 people in 45 minutes. And that engine is being constantly re-engineered. So if I'm engineering a new engine, it's a smaller unit, and I'm designing it so I can just plug it into the airplane as we're learning, as we're improving its performance. So then the point is how it connects to the airplane, the fixed interfaces are the key point.
Mm-hmm.
And that's modular engineering. So it allows the engine teams or any different teams in an organization to constantly iterate without, kind of impacting the whole system.
Yes, yeah, that makes a lot of sense. That's really fascinating. And it means that your team can work independently and work on its own ideas for improving the engine without having to go get approval from the wing people, uh, in order to make your change to the engine or something like that.
That's right.
You work independently, and then yeah, that's really fascinating. That just really crystallized something for me that I've been thinking about.
So the same applies then. So, you can do anything to that engine you want,
Mm-hmm.
as long as the interface is fixed.
Right.
And if you look at that model, that's actually the same what Hayer was talking about. And these modular, they actually design their organizations like small micro companies. So in this aerospace, you have an engine company essentially. So that engine company, their task is to improve the thrust, the performance of that engine, to reduce its costs, to improve its performance every single day. And so they're constantly iterating. And that model is very different than traditional model, which is I'm going to plan for an aircraft that may be built in 10 years' time with this particular technology, which I know is not going to be relevant when it eventually comes about.
What that reminded me of was from the sort of software architecture world was microservices. That if you've got a sort of software system set up where it's the interfaces that matter, then people can iterate and swap in and out little systems. And then and that way the whole thing improves by in a sense not being a whole thing, but being a bunch of connections.
So it's exactly the same concept. So it's the same for hardware. And why is hardware so different? It need not be. Apparently, like engineers, if at SpaceX with some of their rocket equipment, they can re-engineer. So they'll come up with an engineer change. They'll 3D print it, that engine component, and then they'll test it. And if they're in a hurry, they'll launch it all in one day.
Yeah.
So that means that they're able to they can change something in the engine without changing everything. And it gives incredible speed. And it's the same as software. It's the same concept.
That leads me actually to one of the last questions I wanted to ask, which was about failure. And one of the really interesting things about, say, SpaceX is that it's always in the news for rockets blowing up. And I think I say even now there are people who think, oh no, SpaceX sucks. They launched a test rocket and it failed. And that is not SpaceX's attitude towards failure at all. That like it was a test launch. That test launch had an outcome. Let's assess the outcome. In this case, the outcome involved, it blowing up and falling down. But that's not in a very important sense, if it's part of a systemically understood way of doing things, it's not a failure. It's a test outcome. And it seems to me that like a lot of, again, just from reading about it and sort of hearing about big delays, we had a big $10 billion dam that got delayed, who knows how many years in British Columbia recently. It seems like the institutional resistance to failure is what causes the failure. If long delays are failures, or huge cost overruns are failures, it's fear of, and you talked about this earlier, actually, now that I'm putting it together, that like people go into it knowing it's going to fail in certain ways and just accept that because they're worried about some other kind of failure more than the failure that they know.
Yeah. I mean, that's a great example. And actually, one of the case studies in the book is comparing NASA to SpaceX. And NASA's approach to engineering is very conservative.
Mm-hmm.
It's risk averse, and so they will follow a very kind of compliance driven engineering approach, whereas SpaceX is far more adaptive. If you look at the numbers, it wasn't that many years ago. I don't know if you remember, like the Challenger flying, right? So that was meant to be the best way to get things into space quickly, and to launch 1 kilogram into low Earth orbit for that system, Challenger, was I think about $55,000 US per kilogram. SpaceX has got it down. They're targeting $20 per kilogram, and so the cost of getting satellites into orbit, SpaceX has radically rewritten it, and is the most dominant player. So whatever they're doing is working, right? So that's the first thing, and it's radically disrupting. Now, the failure. So if I have a system, what they're doing is they're pushing the system far beyond its limits, and so they will push and push, and they do it intentionally to understand the performance of that system. And so what it means is that it's kind of the right kind of failure, right? So they're failing to learn more about the performance capabilities of the system, and that's all part of how do I get better performance. And it's a completely different culture, but SpaceX is dominating, and that same engineering culture. If I'm honest, a SpaceX system like Starship is far more complex than most capital projects, and the risks are higher. There's more complexity, and SpaceX can do in hours and days what we would take years to do. It's a different engineering model, and it's coming fast to the capital project world.
One last thing I want to talk about on this was I'm getting recollection that we may have talked about this last time too. But one of the amazing things about, say, building a huge gigafactory in 11 months, if one has ever been involved in any kind of construction project, is permitting. And like if you hear us talking about sort of manufacturing a new part and having it in a production line on a car in the same day, you go, how on earth can that possibly be compliant with regulations for industries like that? And I remember years ago hearing about, I think it was Tesla setting up like a battery installation for an electric utility in Australia in 3 months. And the headline news was, ooh, they built the factory in 3 months. And it's like they got the permitting all lined up perfectly to do something like that from like conception to execution in 3 months. That's what blew my mind. Um, and do these? I guess my question is, can these same ideas, when they're applied to software architecture to manufacturing, can they apply to like legal compliance and regulation and things like that, and the way you handle those processes?
Sure. So I met an executive vice president for an energy major a couple of weeks ago, and we were talking about the same thing in these assets, like this offshore asset. And that executive's point was, well, we're just building one of these things, right? It's a one-off. We have all of this compliance to take care of. There's so much the governments want us to do, and they said, well, look, we're not a car maker. We can't make these assets like a factory. And that was true a few years ago, but it's not now. And what I mean is it's possible to create a factory of these massive offshore assets and build them every day.
Hmm.
But that factory is a digital version.
Right.
And imagine now, so I'm an energy major. I have 20 floating processing units, and I've built many of them before. Imagine I'm taking live data from those units, and I have a virtual digital twin of that asset. I can then have engineers essentially say, well, why don't we change? How can we simplify the structures? How can we reduce the number of components? How can we improve performance? So every day they're iterating. It's kind of like a factory, but the factory is not concrete and steel. It's data and processes. So now to your point, let's say that the government comes in and says, look, oh, we have a different way of measuring carbon release, or we need a new set of data that you need to comply with. You can do it instantly. So what happens then is you in your digital assets, you start to run simulations.
Oh.
So what is it we would happen if we did this? What is it so what? And like if you look at the automotive, the compliance to the roadworthiness, previously that was a very long process, but now it's all run through regressions and it's all run through the data. So what we're seeing is the world is changing, where we're kind of jumping between physical and digital worlds, and it's allowing us to do radically new things. And government compliance, I can simulate that. And in fact, it's a much better model. So if I'm building an asset, I could have AI agents, which are only focused on looking at government compliance or government issues. So if something changes in a government regulation, it's plausible as the agent might pop up to some engineer's screen and say, hey, look, you realize something's happened here, something's changed, and that you're no longer compliant. You might want to re-engineer it. That's the new world we live in.
Well, that's absolutely fascinating, and I think a really good place to end. Just touching on how many different areas this kind of different approach to engineering processes can impact. The book is Rethinking Capital Project Delivery: Agentic AI Driven Strategies for the New Era. Thank you very much, Ed, for taking some time out of your morning in Singapore to talk to me in the evening here in Canada.
Hey, thanks, Dan. Thanks for all your great support on Leanpub's fantastic products and services.
Thanks.